So everybody understand the parameters real quick? So again, I have a disc and a ring, and they are rolling along a level ground. They're approaching a ramp. There is sufficient friction for them to continue to roll without sliding. They both start with the same velocity. Does either of these objects roll higher up the ramp? Or do they both go to the same height? Again, they have the same mass, same radius, same speed. So be able to justify your answer. So this most straightforward way to justify it would be to find out how high each of these goes and see if they're the same. By height, I'm not talking length along the ramp. I'm talking about just height. How high up the ramp do they go? So take a minute and try this out. Again, the mass of each is 1.5 kilograms, the radius 0.2, velocity 2 meters per second. You don't have to use those numbers. You can show this by just using symbols. But again, do they go to the same height, or does one go higher than the other? I will remind you that the moment of inertia of a ring is mr squared, and the moment of inertia of a disk is 1/2 mr squared. And we did this problem in class. We just did it the reverse. We rolled them down the ramp. All of you who have something written about torque, that probably won't work. All of you who have something written about energy probably will. What forms of energy, let's just pick one of these, the ring. What forms of energy does the ring have when it's rolling along level surface? But we have more than one kind of kinetic now, right? Does it have both kinds or just one of each kind? I'm sorry, does it have both kinds or just one kind? It has two kinds of energy. It has 1/2 mv squared plus 1/2 I omega squared.
Wait, so I was close.
You were close.
I was close.
But you understand why you weren't correct?
Yes.
Okay. And anybody who has R times F, not close. So let's get rid of that. Clear change in height. So let's just work one of these for a minute. I'm going to ignore all the number parts. Let's talk about just the ring. The ring has 1/2 mv squared of translational kinetic energy. And it has 1/2 I omega squared of rotational kinetic energy. It would be nice if we could put these together somehow. And we have a way to do that. We've talked about this as well. The magic word was it's rolling, so V equals omega times R. This allows a substitution. So for the whether it's the disk or the ring, I can take omega and replace it with V over R. I'm also going to change I. I'm going to put it in terms of the shape of the object. And for the ring, that's mr squared. Now I'm going to do a little bit more algebra here than I normally would. It's squared, so the square goes on both of those. And now if I look, I can cancel the r's out. And I'm left with 1/2 mv squared plus 1/2 mv squared. The r's canceled out. Everybody see that okay? I need you to. So this represents how much energy it has for its center of mass moving, and this represents how much rotational kinetic energy it has. We've just put them all in terms of V, so I can add those together and get mv squared. That's how much energy the ring has as it rolls. Since we're looking at it, might as well just take a moment and redo all that for the disk, because the disk is so similar. Everything that we just did, we're going to do again. The disk has got translational kinetic energy, 1/2 mv squared. It also has rotational kinetic energy, but I'm going to go ahead and just put in the stuff that we did last time, but this time for a disk. So 1/2 mr squared. and then v squared over r squared. Right, so now I have disk and ring. I'm just comparing them. The 1/2 mv squared is the same, but I have a half times a half, and that'll be a quarter. So plus 1/4 mv squared. When I add those together, I get 3/4 mv squared. Now, if you're trying to write notes, if you're trying to do things, can you maybe now go in and fill in the difference of what you have to do here for a thing that's rolling? We're trying to get it all in terms of one of the velocities. So that's what we've done here. There's not a whole lot else to talk about except that that means subbing in the moment of inertia, and it means taking your angular speed and putting it in terms of a linear speed. Now, because it's rolling, it has more energy than if it were just sliding. If it were just sliding, it would only have this amount of energy. And the ring and the disk have the same amount of translational kinetic energy because they have the same mass, same linear speed. But they have different amounts of rotational kinetic energy. One of them is harder to roll than the other. So the one that's harder to roll takes more energy to get it spinning. So since they're both traveling at the same speed, it took more energy to get the to get the ring spinning than it did to get the disk spinning. So the ring has more total energy than the disk at the same speed. That also means that the ring is going to go further up the ramp because it's got more energy. Because we're going to take the next step here and set both of these equal to mgh to figure out how high up the ramp they go. Not any different than what we did before. The only difference was we put them on the ramp. They started with the same amount of energy because we put them at the same height, and they rolled down the ramp. So this is a different question. We gave them the same amount of energy. So you can see a multiple choice question on your next test, right? Where I say I give a hoop and a solid sphere the same amount of energy. Which one rolls higher up a ramp? I'm telling you what to do. Or if I say I give them the same speed, I'm telling you what to do. Right, these are different questions, but they're subtle. This isn't all I want to talk about. I want to talk about one more thing. Let's take one of these guys and put him up on the ramp. So he's up on the ramp now, still moving up the ramp. So center of mass has a velocity that's going this way, and it's still spinning, but it's slowing down. Okay, everybody agree it's slowing down? Could you take a minute and draw in the forces acting on the disk as it rolls up the ramp? Corbin, can you tell me one of the forces acting on the object?
Normal force,
How would I draw that?
perpendicular to the,
And where would I start this arrow?
at the center of the circle.
Okay, actually, no, I'm going to start it at the point of contact. When we're doing forces now, we need to put them where they act on the object because these aren't just free body diagrams, but they tell us about torque too. Does that make sense? Okay. Camilla, can you tell me another one of the arrows I need to draw?
Friction,
How should I draw that?
at the point of contact going down.
Okay.
Down the ramp.
So Camilla says I draw friction like this. Okay. Any other forces acting on the object? David?
Gravity,
How would I draw that? What's that?
the center of mass.
Acting downwards. All right. mg, normal, and friction. One of these is wrong. Yeah?
Is it friction?
Friction's wrong. Why is it wrong? Do you know?
You equals 0.
mu does not equal 0, actually, that's what I'm saying specifically. I say that there is friction. But it's pointed in the wrong direction. And this is something that's going to make you a little bit weary, so pay attention here. Is the friction causing it to spin faster or spin slower? Looking at the way it's pointed now, wouldn't it make it spin faster?
Oh, because it's going down.
This thing is going up the ramp, right? So the frictional force would have to be up the ramp to cause the angular speed to decrease. This, I know, is counter to what you think. You're thinking about an object that is sliding up the ramp. But this object isn't sliding up the ramp. This point here, this point of contact, is at rest with respect to the ramp. Now, I know it doesn't make a lot of sense to you now, but I want you to think about this. The angular speed is getting smaller. It is the frictional force that's causing it to get smaller. It's the only force that can apply a torque to make it get smaller. But think of one more thing. The ring rolled farther up the ramp than the disc. That suggests there had to be a force up the ramp to push it further than the disc. Forces still work here. So believe it or not, friction must have been greater on the ring than the disc, because it's the only force that could have pushed it up the ramp. It's a little weird. We're going to talk more about it tomorrow.